Okay, welcome back. Today we're going to be taking a look at Chapter 3, which is all about probability. Now, probability is always the chance of an event occurring, or more formally, it is the long-term relative frequency of a given outcome. A probability will be any number between 0 and 1. A probability of 0 means that the event is not possible or it will never happen, whereas a probability of 1 means that the event will always happen. We can talk about probabilities that are very basic, such as odds of flipping a heads on the flip of a coin, or rolling a certain number on a die, drawing marbles out of the bag. Very straightforward examples that we can talk about and easily calculate. And then we can extend the idea to more complicated scenarios, like the outcome of a certain election, or the probability of certain medical outcomes based on certain exam results. We can use probabilities to go through all of these things, and in order to make these computations work, we need to understand how different types of probabilities play together. So the first types of probabilities we're going to want to look at is or and and. And this is a way for us to deal with multiple different events. And for this, we're going to use a Venn diagram to go through the idea. So let's suppose here that we've got two different events. Let's go ahead and say we've got event A, and then we've got event B. We're going to let this big purple box be the probability space. This is all possible outcomes that can occur. And we could have the case of neither of them happening, or just A could happen, or B could happen, or both. And if we were trying to do this out to scale, we would try to make it so that the size of the areas was proportional to the likelihood of the given event happening. But for this example, we're not going to need to worry about the size because we're just trying to set up examples. Now, if I'm looking at or, then what we're looking at is the odds that A happens or B happens, or potentially both. So everything that is in A will work as well as everything that's in B. And notice that we are including the overlap. A, B, and the overlap are all included when you're talking about or. So we've got the probability of A or B. You may occasionally see a fancy symbol, A or B, but we'll usually be using the text, the letters or in this class. We can also consider an idea of and. And same idea, we'll go ahead and create a circle for A and a circle for B. When we're talking about and, in the case of the probability of A and B, then we're talking about only the overlap. Both events need to occur in order for P of A and B. Now, already we can create a little bit of math that we can do with these things. We can have that the probability of A or B is equal to. Now, keep in mind, in terms of our picture, what we're looking at there is this entire piece. And what we want to do is we want to build this up out of individual parts. And what we're going to start with is we're going to say, I'm going to start with the probability of A, which we know is just the orange circle. And what we're going to do is we're going to add to that the probability of B. So I'm saying if A or B is going to happen, then I have to consider all the times where A happens, and I have to consider all of the times where B happens. And so visually, we've got these two circles, but there's one big thing that we need to consider. And it's that both of these scenarios have counted the overlap, which means that we have actually counted the overlap twice. And that means that we've actually gathered too large of an area. And so what we need to do to amend that is we will need to subtract the overlap. We will take the probability and subtract the overlap of A and B. And we see what that gives us is if we add the first two pieces on the left together, and then we subtract the overlap, then the overlap is now only accounted for once instead of twice. And as a result, we're able to add together these areas to get the probability of A or B. It's kind of like, what if I gave you a bag of marbles of a variety of different colors and sizes, and I said, give me the probability of pulling out a big green marble. Well, I can find the probability of getting the green ones and the probability of getting the big ones, but both of those chances are including the big green ones. So I need to make sure that I don't count that twice, and the way to do that is to subtract the overlap. There's one other type of probability that we'll want to talk about here, and it's called not, which is very simply the odds that a certain event does not happen. In this case, we'll only need a single circle, and we're simply shading all of the area not included. Now, the whole point of this is that the entire area needs to add up to 1. So the probability of not A, and I can add the symbols. I should add the symbols for A and B. It's an upside down version of the or. And then not A. This symbol we may actually see. It's a little asterisk to indicate that I want to not. Or you may see a squiggle. Is simply 1 minus the probability of A. Because in this way, the probability that A happens added with the probability that A does not happen adds up to 100%, which makes sense because A will either happen or not happen every time we do the event. It can't be a mix of both. We're not working with fuzzy events. It either happens or it doesn't. Now, the next one we're going to want to look at is conditional probability. And the idea for conditional probability is that normally we are considering the entire space. A could happen, B could happen, both could happen, or neither could happen. For conditional probability, we only want to consider possible events given that a certain event has already happened. So rather than having the entire world where sometimes A happens and sometimes A doesn't happen, we're only considering the world where A already happens. And within A happening, there's a chance of B happening. The overlap is still present. But all of this other part, the part where B did not happen, the part where B happens but A didn't, we're not considering it. We're only considering the part where B actually happens inside of A happening. And what we can do here is we can create a fraction. The terminology here, the notation, is we're looking at the probability. Let's write it over here. The probability of B given A. For this one, we'll also frequently use the shorthand notation, which would just be a vertical slash. This is the probability of B given A. And a good way to think about this is that this is like a fraction. It's the probability of like B over A, kind of. Given that A happens, what are the odds that B happens? And by thinking about it in this way, we can understand the notation and the formula very easily. The probability of B given A is going to be the overlap divided by the entire circle, which means I need to take the probability of B and A and divide it by the probability of A. What are the odds that both B and A happen? And also, what are the odds that just A happens? Not caring about B. Maybe B happens, maybe B didn't. Divide those two together, and you get the odds that if A happened, B also happens. An example here would be, what are the odds that if I pull a green marble from the bag, it's a big one? Now that we understand the different types of math that can show up in probability, let's take a look at some classifications of what type of events we can have. The first one is called independent events. And independent events, we've got all of these fancy formulas, but basically independent events are events that do not depend. They're independent, they do not depend on each other. For example, I flip a coin and also I roll a die. The outcome of the coin is not going to affect the outcome of the die, and vice versa. It doesn't matter what happens with one of them, the other one will be completely unaffected. And that's the idea of independent events. And there's a lot of different math that comes out. The first two pieces come straight from the definition. The probability of A given B or B given A is just the same as the probability of one event not considering the other, because A doesn't depend on B. So the probability of A, given that I know that B happened, is exactly the same as the probability of A if I know nothing at all about B, and vice versa. And what this gives us is this very cool piece of math. Because recall the formula for conditional probability. We said that if we have the probability of B given A, then that will end up being the probability of A and B divided by simply the probability of A. Well, the probability of B given A, if the events are independent, is simply the probability of B. Which means that we can then say I have P of A times P of B by multiplying by the denominator is equal to the probability of A and B. What does this mean for us? Well, if I know that two events are independent, maybe the problem says so, maybe I understand that the events have nothing to do with one another, then I can go ahead and I can use this formula to more easily calculate the probability of A and B happening at the same time. And I really want to stress here, this is very important. This only works if we know the events are independent. If the problem does not say, or if we don't have a reason to believe they're independent, then we should not assume that they are. Very often, two things will look like they might be independent, but they actually do depend on each other a little bit. So if it doesn't say, we don't have a good reason, don't assume that the events are independent. The other type of event we'll want to look at is mutually exclusive events. These are very straightforward. They can't happen at the same time. I roll a die once, and it simultaneously rolls a 3 and a 5. No, that can't happen. It's not possible. It only rolls one number. It's a 3 or it's a 5. It's not both. And as a result, the probability of both events happening is simply 0. And this formula has a small typo. This should say or here. The probability of A or B happening is that the probability of A plus the probability of B, because the piece that's missing from the original formula is simply subtracting away the probability of A and B. But we can ignore this part because it's just 0, so you don't have to worry about it. Okay. Now that we've got all of these tools under our belt, let's go through a couple of examples. First, let's look at this case. We're looking at an event C that's taking an English class, and D is taking a speech class. And we're considering this for all of the possible students in a given curriculum. And it gives us a bunch of different probabilities, P of C, D of C given D, and of C and D. And here's going to be our questions. Are C and D independent? And 2, are C and D mutually exclusive? And in both cases, we'll want to justify with a formula. Let's first take a look for number 1 to see if they're independent. If they are independent, then the probability of C should equal the probability of C given D. In other words, I shouldn't care whether or not they took a speech class or an English class if I'm looking at one as opposed to the other. It shouldn't affect it. And here I see that it doesn't. The probability of C and the probability of C given D are exactly the same. I can also verify that if I take the probability of C and multiply it by the probability of D, I should get the probability of C and D. And we can check that very quickly on our calculator here by taking the 0.75 and multiplying it by the 0.3. It does come out to 0.225. So we're good. These events are independent. For number 2, are the events mutually exclusive? Is there any chance that you are in a speech class and an English class? Yes, because there is a probability that C and D happens. It's about 22%. So since this probability of C and D is not equal to 0, then no, we are not mutually exclusive. Let's go through one more example today. More complicated one this time. We'll need some extra space. We're taking a look at the following information. 48% of all California registered voters prefer life in prison without parole over the death penalty for someone convicted of first-degree murder. Among the Latino California voters, 55% prefer the same option. Furthermore, it tells us that 37.6% of all Californians are indeed Latino. We're going to define C to be the Californians who prefer life in prison over the death penalty for this specific crime. And we're going to let L be the Latino Californians. Now we're going to find and interpret all of these different pieces. And then the same problem as last time, we're going to figure out, are these events mutually exclusive? And are they independent? So first, let's fill in the different pieces. P of C, P of L, those should be easy. We can find them in our problem. It says P of C is 48% of all Californians, it says. So that'll be 0.48. We're always giving our answers here in decimals rather than in percents. Similarly, it tells us P of L is 37.6%. So that's 0.376. It gives us one additional number here, 55%. So that will be P of, let's see, it says among Latino voters, 55% prefer life in prison over death penalty. So that's saying, given that the voters are Latino, this is the probability that they prefer life over the penalty. So that's the probability of C given L. The probability of them feeling a certain way about the policy, given that they are a Latino voter. And that is equal to 0.55. It's now asking us for two other pieces of information. The probability of L and C is next. Now, you may be tempted to multiply P of C and P of L here, but this only works if the events are independent, and we don't know that they are. So we don't want to simply multiply probability of C and probability of L. Instead, we'll want to think about this formula, which is always true, that the probability of C given L is equal to P of L and C divided by the probability of L. Remember, we'll think of this C given L as like a C over L type thing. And so, what we'll need to do here is we'll need to use this formula, and if we multiply the P of L to the other side, it gives us that the probability of L and C is equal to P of C given L multiplied by the probability of L. This we can do. That will end up being 0.55 multiplied by 0.376. Putting that into our calculator, we obtain 0.2068. About 20% of voters are both Latino and prefer life in prison over the death penalty for this specific crime. Finally, it asks us to find the probability of L or C. And once again, let's not assume that it's mutually exclusive. We'll say that the probability of L or C is the probability of L plus the probability of C. And then remember, we need to subtract the overlap. So we'll need to subtract the probability of L and C. If we knew the events were mutually exclusive, we wouldn't have to subtract the overlap. But in fact, at this point, we know that they are not mutually exclusive because look right here, the probability of both things happening is not 0. There are some voters that are both in favor of this policy and also Latino. So there is an overlap. They are not mutually exclusive. We'll simply add them up here. So that means we have 0.376 plus 0.48, and then minus the overlap of 0.2068 that we calculated in the previous part. So let's add that all up. 0.376 plus 0.48 minus the overlap of 0.2068 gives us 0.6492. 64.92% of voters either are Latino Californians or they prefer life in prison over the death penalty for this crime, or both. We are including both here. We're just not including the overlap twice. We're only subtracting it away once because it was already included twice. Finally, are they independent? If they were independent, then it shouldn't matter whether one thing is true when looking at the other. And take a look at these two probabilities. The odds that they're in favor of this certain policy changes based on whether or not the voter is Latino. So no, they are not independent because P of C is not equal to P of C given L. They should have been equal. Similarly, are they mutually exclusive? No, because the P that L and C happens is not 0. Only if a probability of the overlap is 0 are the events mutually exclusive. That's all we've got for today. We'll see you guys next time.